Okay, Unit 1 is all about inverses. So today we're going to talk about the relationship between a function and its inverse. So I challenge you to do this note section on your own, and then you can use the answer key to check. And if you miss something, then come back to the video notes and then you can go ahead and watch it if you need to. But you should be able to do most of this on your own. So 4.5 says, what's your pace? Chandler and Isaac both like to ride bikes for exercise. They were discussing whether or not they have similar pace so that they could plan a time to bike together. Chandler says that she bikes about 12 miles per hour or 12 miles in 60 minutes. Isaac looked confused and said he does not know how many miles he bikes in an hour because he calculates his pace differently. So for question 1, using Chandler's information, determine the independent and dependent variables. So let's go ahead and look back at the piece of information they gave us. They said that she bikes about 12 miles per hour or 12 miles in 60 minutes. So the independent variable in this case, since it's miles per hour, remember it's rise over run. So the rise is your y and the run is your x, which in this case would then mean this is time. And we're going to go ahead and use minutes. And the dependent would then, of course, be the number of miles or the distance. So because this is x and this is y, because remember y depends on x, so it depends on what you plug in. Since Chandler uses time to determine the distance she travels, determine how far she'll go in 1 minute. So we have 12 miles per 60 minutes is equal to the number of x miles per 1 minute. So if we solve this, you can cross multiply because it's a proportion, or really just do 12 over 60, and we end up with x equals 12 over 60, which as a fraction is 1/5, or as a decimal is 0.2. So we're going to go ahead and use the fraction form. So 1/5 of a mile in 1 minute. Fill in the table of values to determine the distance Chandler will travel in 5 minutes, 10 minutes, 20, etc. So for the first one, we just said 1 minute was 1/5 of a mile. So if 1 minute's 1/5 of a mile, then we know that 5 minutes would be 1, 10 would be 2, 4, 6, this would be 12. Where are we getting that from? Because it's 1/5 times the minutes. So 1/5 times t would be my equation. So it says for the question number 4, write the equation for Chandler's pace using time in minutes as the independent variable and distance in miles as the dependent variable. So for this one, we would get 1/5 t. Could you write that as 0.2? Yes, but again, I like to use fractions. So then we're going to sketch a graph. It says whose domain goes from 0 to 120. So on here, I'm going to want, since we're going from 0 to 120 for my domain, I'm going to go by 5s as I'm counting on the x-axis scale. So for this, if the domain's from 0 to 120, which again, I went by 5s for my scale, I only wrote out the 10s, and then that means we want to figure out what's the highest range value that we have. So if I do d of 120, remember this is just your function notation, we're just using this equation up there. We get 1/5 times 120, which is equal to 24. So that means that we have the point 120 comma 24. So the highest range value we have for this domain is 24, which is right here on my graph. And for this, remember that why aren't we graphing any of the negative values? Because we're talking about distance and time. So that's why we're only using the first quadrant. So if this is our domain again from 0 to 120, that means that the range we just found is from 0 to 24. and I'm using brackets because we're including the values. We can use this table right here that we had to go ahead and graph. So if I plug in 0 into my equation, I would get 0 out. If I plug in 5, we know that's 1. And then we have 10 is 2, and 20 is 4, and 30 is 6, and 60 is 12. And then I would use my ruler to go ahead and connect each of these points. And so now we have our graph. And again, we're only using quadrant 1 because we can't have negative distance or time. And so that's it for this portion. The next question says, Isaac says he calculates his pace differently. He explains he can bike 5-minute mile, meaning that for every 5 minutes he has traveled 1 mile. So it says, how is this description different from Chandler's description of her rate? So if you'll notice, the independent, which is of course your x, and dependent, which is your y, variables have switched. Could have also said your domain and your range have switched. Those all mean the same thing. Since Isaac uses distance to determine how long he has ridden, determine how long it will take to travel distances in the table below. So we know if the distance is 1 mile, it takes him 5 minutes. 2 miles would then be 10, 4 would be 20, 25, 30, this would be 60, and how do we know? Because we're taking 5 times d in this case, 5 times the distance. So t of d is equal to 5 times d. Then we're going to go ahead and sketch a graph. So for this one, thinking about what we just had in our other graph, we graphed it from 0 to 120 for the domain, but remember we're switching it, so it's going to be switched on this one. So for this one, we are using our domain now from 0 to 24, and the range is going to be from 0 to 120. So I'm going to count by 2 on this scale. Actually, let's count by 1s, but I'm going to write just the 2s, and then I'm going to count by 5s on the y-axis. Okay, so that I just labeled my graph. And again, how did I know that the domain was 0 to 24 and the range was 0 to 120? Because remember we said in this question here, the independent x and dependent variables was switched. So if we go back down over here to this graph, if we're switching those variables, then we're switching our axes, what we're labeling them as well. So that's how I knew. So going back here, we can go ahead and plot our points. So we had 1 and 5, 2, 10, 4, 20, 5 and 25, 6 and 30, etc. And again, I'm just getting that from these table of values up here. And then I can use my ruler to connect the points. And so now I have my graph. So make sure you always label your x and y axis when you do that. So in reality, both Chandler and I are biking at the same pace, which means their functions would be exactly the same if they had not switched their independent variables around. When this happens, the functions are said to be inverses of each other. So inverse functions of each other. When this happens, the original function can be written as f of x, and the inverse function can be written as f inverse of x is how we write that. So I'm going to make a little note. This is read as f inverse of x. So for question 10, it says using the equations, tables, and graphs for Chandler and Isaac, make a list of observations of what happens when you have two functions that are inverse of each other. So one thing we noticed is we switched the independent and dependent variables. Or we could say we switched the domain and range. And you'll notice that if we look at the equations, so this one was T of D equals 5D, and Chandler's was D of T equals 1/5 T. If you look at the slopes, notice there are reciprocals of each other. So this is 5 and this is 1/5. So question 11 says, why do you think inverse functions have these characteristics? So your answers could vary here, but they have these characteristics because they undo each other. Given the examples below, determine the values for the inverse function in the same formats. So again, here is a table. And if we want to notice this one saying to find the inverse function, so this is the inverse. We said we switched our domain and our range, switched the independent and dependent variables. So that means we're going to be switching our x and our y's. So that means that these values are going to become the x values. And these values become our y values. And that's it. So those are our new points. So again, we switch x and y values, or independent and dependent. So now for B, we are given a graph and we want to find the inverse. So if I want to find the inverse, I can go ahead and make a table of those points that I can see. So it looks like I have the point, we'll do this one first, 1, 6. Then I have the points 0, 4, -1, 2, -2, 0, and then this point here would be -3, -2. So then the inverse, so x, and I'll use this one as f of x, or inverse of x. So this would be now 6, 4, 2, 0, -2. This becomes 1, 0, -1, -2, -3, because you switch the x and y values. And you can go ahead and graph. So we have the point 6 in 1, 4, 0, 2, -1, 0, -2, and -2, -3. And we can use our ruler to connect the dots. And now we have our inverse graph. Another way we could have done this is we could have looked at the slope of the line and maybe the equation. So if we look at the line that's in red, or f of x, the slope is going up 2 over 1. So for this function, f of x is equal to, we're saying this one's f of x. So f of x is equal to 2x plus, and the y-intercept is at 4. And if I look at the inverse, so f inverse of x is equal to, the slope of this line goes up 1 over 2, so 1/2 x, and the y-intercept is at -2. So you notice that the slopes here are reciprocals of each other. And then you could use that to pick a point and go up 1, or however much the slope is. So different ways of looking at it. And something else that we haven't talked about yet is that this point right here, inverses are reflected across the line y equals x. So you can see if we draw the line of reflection in, you can see that this is a reflection across the line y equals x, and that is true for all inverse equations. Why is that? Because when you doing the inverse, you're undoing what you did for the other equation, so it makes sense that you would just get x back, and I can kind of show you that. If I were to plug this whole equation in here in for x, you would notice you're only going to get x out. And we'll talk about this more in a different lesson, but just to show you real quick, 2 times 1/2 x minus 2 plus 4. If I distribute this 2 here, 2 times 1/2 is just 1x. 2 times -2 is -4 plus 4. And notice that you're left with x. And that's always going to be the case when you have an inverse functions. When you plug it into the other equation, you should always get x back. And again, we'll talk about that later in a different lesson. All right, so let's look at the next one. It says Bernie owns Bernie's bike shop and is advertising his company by taking his logo and placing it around town in different size signs. After creating a few signs, he noticed the relationship between the amount of ink he needs for his logo and the size of his sign. The table below represents some of the signs Bernie has created and the relationship between the amount of ink versus needed versus the size of the sign. Complete the information below to help Bernie see the relationship. Don't forget to label your graph. So it says for question 1, what do you notice about the relationship between the input and output values in the table? So if I look here, notice here's the input and these are the output values. And I can see this is 3, 9, 4, 16, 2, 4. So it looks like the x values are being squared. So we have 3 squared equals 9, 4 squared is 16, 2 squared equals 4, etc. It says write an equation in function notation to represent this situation. So instead of writing y equals, we use f of x. So f of x is equal to x squared. So it says for this table, we're going to have x squared here. So for question 3, it says graph the function, identify the domain and range of the function. So if we graph this table, so if we think about it, if we have no sign, then we don't need any ink, so we can start it here at 0, 0. If we have, this is 1, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16. And if we're squaring it, we know that this is a quadratic function, and so it makes a parabola shape. So it's going to give us this right here. We can't have negative length of a sign, and we can't have negative ink, so that's why I'm not going to draw the other side of the parabola. We're only having the positive side in quadrant 1. So x is, of course, the length, and y is the amount of ounces we needed for the ink. So ounces for the ink, and the length is for the length of the sign. And so again, we're only using quadrant 1 because you can't have negative length or ounces. And so the domain is going to be from 0 to infinity. And then the range is also 0 to infinity, which is half of our parabola. So for the next part, it says, using the information about Bernie's bikes, complete the information below for the inverse of the function. So we have ounces needed. So if we have 9 ounces, we know that the length of the sign would be 3. 16 is going to be 4. 4 is 2. And I'm getting this from our other table, 36, 6. 225 we know would be 15. So that came from our other table because remember we switch our x and our y's in our table. And so for this one, if we have these values, Then what did I do from this side to get to this side? So we're taking the square root. The square root of 9 is 3. The square root of 16 is 4. So we're taking the square root of x. So we could say g of x equals the square root of x. It's the inverse of f of x. So another way we could write this is f inverse of x equals the square root of x. We're going to graph the inverse and identify the domain and the range. So now we can have 0, 0. We have 1, 2, 3, 4 is 2. 9 is 3. 16 is 4. I only picked values that we could take the square root of nicely. So again, we know that the x now is the ink, the amount of ink in ounces, and y is the length of the sign. And again, notice that we are only using the positive side. So the domain is 0 to infinity, and the range is still 0 to infinity. Now I just want to make a note real quick that if you were to solve this equation right here, x squared equals 49, we know to get rid of the power of 2, we learned last year that we take the square root of both sides. And when you take the square root of both sides and getting rid of that even power, you need plus or minus. So if I take this plus or minus square root of 49, I get plus or minus 7. And so we know that works because if we were to check, if I were to do negative 7 squared, that equals 49, and positive 7 squared equals 49. So we have two solutions, but remember that we're talking about the context of the problem. We can't have a negative length of the sign, we can't have negative ounces. So in this context, that's why we're only using the positive square root. But if it's not a context, you're just given the equation, you would want to use the plus or minus, such as, let's go ahead and look at example number 5. It says graph f of x equals x squared minus 1, and we're going to graph the inverse, f inverse of x equals plus or minus the square root of 1. So for this, we're not using our calculators to help us remember, so when we are graphing, we can just make a table. So this is going to give us a U shape, and if you recall from last year, we have our vertex form of parabola y equals a times x minus h squared plus k, where the vertex is at h comma k. So I can see right away that the vertex here is at 0, negative 1. So remember, each side of your graph of the parabola should be the same. So I'm going to pick 2 points to the left and the right of that. So we have negative 1, negative 2, and then 1 and 2. So if I plug into my graph negative 2 squared is 4, minus 1 is 3. If I plug in negative 1, I would get 0. If I plug in 1, I would get 0, and this would be 3. So on my graph, I have 0, negative 1. Then I have the points 1, 0, negative 1, 0, and 2, 3, and negative 2, 3. And that gives me my shape. And if I were to plot another point, this would be at 9. Or, sorry, not 9, 8. That's off. There we go, 8, because we moved down 1. All right, so that is my graph of f of x. And if I want to graph the inverse, now that I have my table, f inverse of x, I take these y values and they become the x values. And the x values become the y values. And I just have to go ahead and plot them. So now I have 3, negative 2, 0, negative 1, negative 1, 0, 0, 1, and 3, 2. I would also have the point 8, 3, and 8, negative 3. That's from this point here and this point here. And so I can go ahead and graph. And so that would be my inverse. And let's go ahead and look at the domain and range of each function. So for the first one, the domain, we can see I can plug anything in for x, so it's all real numbers. So negative infinity to infinity. The range, however, I cannot plug in or get all real numbers out. It starts at the lowest value, which is -1, and it goes to infinity. And so for this next one, and over here, let's go ahead and write down the vertex. So the vertex was at 0, -1. For the next one, we are going to go ahead and use this to help us. So notice that the vertex, the x and y switched, is at -1, 0. The domain comes from the range. So the domain, notice, starts here and goes this way. So bracket -1 to infinity. And that's because, remember, if we have a radical in our equation, we can't have negative numbers underneath a radical. Those are imaginary. And the range then would be all real numbers, negative infinity to infinity, because if this is the domain, that becomes our range. Something else I didn't ask us to do, but if I were to draw the line y equals x right here, notice that the graph would be flipped over, so it's reflected across the line y equals x. So for this equation down here, you should be able to do this one on your own. So you could pause the video, do the problem, and then unpause it and check your work. So for this one here, it says we want to graph f of x and f inverse and identify the domain and the range. So if I look at the first part, we're going to go ahead and make a table, x and f of x. Here I can see that the vertex is going to be at -3, 0. So I'm going to move around from that point. So I'm going to start here in the middle, -3, 0. So I'm going to use then -2 and -1. And the other direction would be -4 and -5. So if I plug -5 into this equation, -5 plus 3 squared would be 4. -4 plus 3 squared would be 1. -2 plus 3 squared is equal to 1, and this is 4. We can go ahead and plot that then. So -1, 2, 3, 0. And again, we learned that last year. That's from our quadratics unit. We have -1, 2, 1. Then we have this point as well. And -1, 4. So that means this point is also there. If I were to pick another point, I would have 0 and 9 if you wanted to be a little bit more accurate. And so that, oops, gives me my graph. Sorry to kind of mess up the little U shape right there. Then, of course, for the inverse, we take these values and those become our x's. And the x values become our y values. And we can go ahead and graph. So on my graph, I have 0, -1, 2, 3. 1, -4, and 1, -2. And then we have 4, -5, and 4, -1. And if we use this point and this point, we would have 9, -6, and 9, 0. And that is my inverse graph. We can go ahead and look at the domain and range. So for this graph, the domain is all real numbers because we can plug anything in for x. And the range starts at 0 and goes to infinity, so bracket 0 to infinity. And so then for my inverse, the vertex is 0, -3. And remember that the range becomes the domain. So bracket 0 to infinity, which you can see on your graph, starts here at 0 and goes this way to infinity. And then the range is all real numbers, so negative infinity to infinity. Make sure you're using your interval notation. And we weren't asked to do this, but again, this is the line of reflection, y equals x. So if I was to fold my graph in half in this line, you would see that this parabola would match up to this one here. Okay, we're done.